Well, greetings, Mr. Kolazar's class. Going to look into video number 5, and it's going to talk about reversible chemical reactions and our idea of chemical equilibrium. Now, our main idea is products can collide and reform the activated complex and become reactants. This is going to be called a reversible reaction. Forward and reverse reactions are going to reach a state of equilibrium. So what we mean by that is, our products can collide to make our activated complex, or they can switch back from that activated complex to become reactants. So we can kind of move both ways in our chemical reaction. So a reversible reaction, chemical reaction that occurs in both the forward and reverse directions. So we could have, our reactants, nitrogen and hydrogen, are going to produce NH3 and a little bit of heat. Or this reaction could go the opposite way, where we could have ammonia, let's start with, is going to produce hydrogen and nitrogen. So in a reversible reaction, you will a lot of times see the symbol look this way, or you'll see a symbol look this way. And these both signify a reversible reaction. So one that can go both ways. Not all reactions are reversible. Certain reactions, it goes one way and then that cannot be returned back the other way. Now, a reversible reaction, our potential energy diagrams, we're going the opposite way. So once you've started out with your reactants to form products, we could go from our products and back to our reactants. The activation energy is still at the same point. The amount of energy is going to be different depending on where you start or end. And then our heat of reaction, however, is going to be the same, except it's either going to be positive or negative. And then our catalyst line, again, lowers that activation energy. It does not change our heat of reaction. So a reversible reaction, when a reversible reaction takes place in a closed system, equilibrium is established. And what we mean by equilibrium or balance is the rate of the forward and the reverse action or reaction are equal. Now, amounts of reactants and products become constant. When they become constant, they usually do not equal each other. It's not 50%, 50%. So it's not 50-50, but it's going to be constant, is what we're going to look into. In our closed system, our reactants and our products never leave the system, so they're allowed to get to that point of balanced out. So an example of this, we're showing our reversible arrow here. So we can go back and forth between nitrogen and ammonia, or nitrogen hydrogen to produce ammonia, and that reaction can go back and forth between those two. Now, what we're going to look at is, this is our beginning part. So at A, which the reactions take place at point A, we're going to put kind of an A as our starting point right here. And at point A, all reactants, no products. So NH3 is down here, 0 NH3. And N2 and H2 are both at higher concentrations. We have no NH3 yet to begin with in our model here. Now at point B, we're starting to move from N2 and H2, and we're starting to move to more NH3. Now as we move to more NH3, we'll start and we'll be kind of at about here during our reaction. And as we get there, more reactant is turning into products. So we're going faster towards the products. Starting to push to make those products. Now once we get to point C, C is going to be where we start getting to that equilibrium. So we're balancing or equaling out here. And then finally, as our reaction continues, we get to our complete balance point where the amount of products we have and reactants we have all stay constant the rest of the way. As more product is made, it's going to shift back to reactant. As more reactants made, it's going to shift back, and we're going to get to our equilibrium, or a constant amount of reactant and products. Remember, they're not equal to each other, so this will be our point D. Will be here, where they're not equal to each other, but they're at a balanced amount called equilibrium.